Now, why is this larger computational time acceptable, right? Because ultimately you know that we want to do these things very fast, right? And like I told you, if we have all these signals available at t equal to 0, I would rather do it like this, right? So the answer to this is, we have to go back to the fundamental assumption that we made here. We are assuming that R0 to R1 are all populated at t equal to 0. But how is that even possible? For that to happen, again, remember that I can do that only if I have 32 into 16 512 signals available as input, and then I write into these registers at t equal to 0. But if they were available at t equal to 0, I would have rather done it the combinational way and finished it much faster. I don't need so many 16 clock cycles and all to do this whole addition process, right? And therefore, we need to basically go back and understand what happens if the data that could be admitted into this block was only 32 bits at a time. Okay, so therefore now I am going to assume that my block here, right? Maybe I'll first make a copy of that so that it's easy for me to edit and redraw. Okay, let me copy this. Okay, so this I am going to now say that my inputs to this block can also come in only 32 bits at a time. So therefore, my data can come in 32 bits at a time. So this is my answer, 31:0. My clock, my data here also is going to be exactly 32 bits at a time, right? So I'm going to move this slightly to the right so that I get more space, right? So data of 31:0, right? Now, if the data is allowed to come into the system only one 32-bit number at a time, then how many registers do I need here? How many registers do I need, or do I even need any register at all, is the real question that we have to ask ourselves, right? So for example, if I had these 32 bits coming in like this, I could simply remove this whole thing, right? This whole thing I will just remove, right? And I will simply redirect this data bus directly onto the B bus, right? I could just redirect this entire thing to the B bus, and therefore I could have, these interesting, this whole operation performed in exactly the same way. So what we are assuming now is the data itself is going to come in like this. This is my clock period. Okay, so my data itself is going to stabilize like this. We are assuming that that is taken care, right? And what we are going to do is, we are going to basically say this is my data clock, and this is data state 0, D1, D2 and so on, right? All of this has to change before the setup time of the sampling edge, otherwise that data can, you will end up in some trouble. Now of course the only problem is, it is very difficult for us to control the primary input and impose conditions that the primary input should not change while this addition is happening, because let's say that while this clock is happening, if this D0 changes to D1, right, very early, then it could actually just race through this adder and it will cause a problem. So therefore, putting one register inside and clocking it is very useful because it allows you to synchronize the data. So the data comes in here, I have one register and this register output is permanently permanently connected to the B data bus. So all we are doing is data can now change, but only on the rising edge of the clock. So here also there is a clock which is going to control this write into this register, just like we did here. So when the rising edge comes, data will next get written onto that, then it will appear on the bus and then it will continue to do this evaluation, right. So that's why it is good to have at least one register in there in order to synchronize the data to the clock edge appropriately. So now how does this whole evaluation of this, timing diagram of this system look like? Basically your B bus is now going to get the data on every clock edge, right, and therefore you are going to say, so what is going to happen? You have the clock like this, and data, right. So this is going to go to just to show you that the data can actually change at any point. I am going to draw this a little different. So this is D0, this is D1, D2, D3. Of course, this data should not change. If you want that to capture, it should always settle before the setup time of the rising edge. Okay, so D4. So this data is appearing at a certain rising edge, and then your B bus, right, 31 colon down to 0, I will not mark that, is going to get this whole thing so in the previous clock edge the data had stabilized to D0 correctly before the setup time, and on the rising edge it is going to appear in the B bus. So this is, now the key point is, it doesn't matter what happens to the data, this data will be synchronized to the clock perfectly and will be available appropriately for computation. So D1, D2, so this D3 for example came much earlier, but it gets sampled only at the clock edge, and therefore this will change to D3 here, right, assuming that this change to D4 also is before setup time. You will all be in good shape here. Data has come in like this. This is my B bus, right, and what you now need to do is, of course, assuming that the counter is in sync with this data coming in appropriately, you will be able to go through 0 to 16 and then appropriately get the output after a fixed number of clock cycles. Okay, so that is one side of this story, where technically just one register I am able to do all these operations. Now it's very interesting that we also chose to hard code this operation here, right. We chose to hard code this operation to an addition here. So why should that be the case? So technically that is also not necessary, right, and I would like to rethink that strategy as well. Okay, and I am going to call this a general arithmetic logical unit, ALU, which can do any operation. Put that here. Okay, now in this case I am going to choose 4 random operations. Okay, ALU can do 4 things: 0, operation is it can do addition, 1 is it can do subtraction, 2 is it can do AND operation, bitwise AND, that is you take the A bus, B bus and bits A0, B0, bits A1, B1, like that bitwise ANDing you do, that is what I mean by AND. 3 and I will do bitwise OR operation. Now in order to tell this ALU what operation to perform, I need to give it a code. I need to tell it do this particular operation, and therefore I need 2 bits here, OP of 1:0, to decide whether it is one of these 4 operations. So this is what the operation I am going to call this 0 0, 0 1, 1 0 and 1 1. Okay. So technically I can bring this opcode bit out like this, right? The operational operation bits 2 bit 1:0 out like this. And of course again we suffer from the same problem that we would suffer from what we saw with data if we didn't put a register, and therefore we might want to register this, right? We might want to register this using a clock. There is an OP, right? And therefore what we are going to do now is, along with the data that is coming in, right, the clock is a primary input, so it is coming out like this. So along with the data that is coming in, right, what I can technically now do is, so what I can technically do, in fact now I already have that waveform here, what I can technically do is also to define an operational waveform, the operation code that has to be performed inside the ALU. So for example, I could do this addition, subtraction, right, and OR, right. So this is operation 0 0, 0 1, 1 0, 1 1, right. I do all this operation. So what does this basically do? It is going to do, first D0 comes in, right, it will do D0 plus 0, then it will do D0, it will do D0 minus D1, right, D0 minus D1, because if you look at this, after the reset we are going back to the answer is being fed back as an input. So you will get D0 as the answer first, then you will do D0 minus D1, then that answer you will do a bitwise AND operation with D2, then a bitwise OR operation of that result with D3 and so on, right. So this is basically very nice, and we are able to do all of these things very nicely, okay. Now the point is that in general we are assuming that we are operating only on this answer by default. Now why should that be the case? That is not necessarily the case, right. So in fact a general mathematical operation takes 2 operands as input and you get one set of outputs, right. So in general even this assumption need not be true, okay, and technically therefore the second operand can therefore come from anywhere. Now where should this second operand come from? So let us look at that, right. So now I am saying I want to modify this system a little more, make it slightly more generic by doing something else on it. What is it that I want to do? Let me show you, okay. This second operation, I am not interested in bringing this from this thing. So let us assume that I have another data bus which is 31 down to 0, right, and I am going to fix another register R1 out here, which is going to go. So now I don't need all of this, okay. I am going to say this is going into the A bus. I have 2 registers. In fact, now in this system I have 3 registers, R0, R1 and the answer register which is at the output, right, and all of these are going to be controlled by the clock. So I would call this data A and this one as data underscore B. So the A bus, B bus in some sense has been brought out as primary inputs for this compute system, okay. So what do we have now? We have 64 inputs, right, 32 outputs and of course one more thing which is called the clock, and we also have this OP, right, we have this OP which is basically coming from outside, okay, in general. So therefore what we have now is slightly more generic, okay. I can do, for example, I can feed 2 numbers on the A bus and B bus, and depending on the opcode I can choose to do any operation, any of these 4 operations on that, and the answer is available there, right, in the answer register out there, okay. Now if I want to build on this more generically, what I would want to do is also to have an operation where I can use the answer register also as an input, like the earlier case where earlier we had hard coded that, but now I want to be able to use that as an input, as well. More generically, if I go one step, look at it from one step back, what I want to be able to do is, I have 3 registers with me, okay, and suppose I can technically read from any of those registers and write back to any of those registers. So that is the key point here, that now we have register R1, R0 and R1 in which we are writing some input data, it is being read, but the ALU never writes back into R0 or R1. Likewise, the ALU will write into the register, let us say answer, right, this is my answer register, and you are going to read that out to the primary output. But there is no way for us to write into R0 or R1, right, or for the data bus A or B to write into the answer register directly. So in general, what we want is a bunch of registers. We want a bunch of registers R0, R1, R2, something, right, RK minus 1, right, K registers I want, into which you can either write or you can read from them, okay. So that's the basic idea that we want, and that is what leads us to the concept of the design of a register file, okay. So this is the register file that we want to now design, and we are going to list out the properties of these register files. So what we want, our wish list. Wish list is, in order to do any mathematical operation, typically you would need 2 operands, right. In some cases you could do with 1 operand, but otherwise you need 2 operands, right. You need 2 operands. Operands to the ALU, okay, and the answer that we get from the ALU, we should be able to write back into any of these registers, okay. That means you have to be able to do 2 parallel reads. This is what this thing means. and you want to be able to write back the answer, ALU answer, into any register. Okay, that means the answer is only one answer from the ALU. Therefore, you want to be able to do one write. Okay, and what else do we want? Really, this is exactly what we want, right? Earlier we had hard coded all these to just some fixed operations for these registers. So this, if you, in the context that we have, what I am saying is, I want to make it, I want to take these three registers R0, R0, R1 answer, and bunch of three registers with these properties. So I should be able to choose any two of these as arguments to my ALU and write back into any of these. Now if I am able to do this, then I can do the previous operations that I wanted, you know, this accumulation of sum or whatever it is, along with many other operations in a very efficient manner. Okay. Now, okay, so does this mean that I can, you know, finish all my operations, any kind of mathematical operation I want or any program that I want using just two registers or three registers? Well, the answer is no, right? Like I told you, we came up with this number 3 because you have two input operands to the ALU and one output. However, many times you might want to store an intermediate result of an operation somewhere till you finish some other operation, because the ALU, right? See, for example, you know, we did some earlier cases, right? If I want to do A plus B and C minus D, then what do I need to do? I need to feed A and B as operands first to the ALU. The answer I get from that, I need to store it somewhere. Then I will feed C and D as operands, and then of course I have to change the operation to subtraction. Then store that answer somewhere and then do a bitwise AND on these two numbers, right? Therefore, it seems like I need a couple of more registers for me to store these intermediate results and handle. So it's not sufficient if I use 3. So the x86 processor managed to do this with just about 4 general purpose registers, the SI, DI and stuff like that. So typically with just 4 general purpose registers, the x86 was able to handle this, and that is why it is possible to do it with such few registers as well, right? But other microprocessors can expand this register list to something like 30, 31 also, it's 32. It's not that difficult for you to implement the register file because it's not going into some MB or KB, right? It's actually just a bunch, like maybe 30, 40 registers you might use, right? At most along, and each of them is a 32-bit register. So therefore, I will say that the wish list R2 all the way to R31. Let's say I want to implement a register file like this, okay? Which is 32 bits each, and there are 32 such registers, right? Now, what is the advantage with this process of allowing the data to be written into any register either from outside the data bus or from the ALU's result? The advantage is I don't need two data buses, right? So in some sense, what I can do now is define this register file like this. This is my register file. My data bus from outside, right? My data bus from outside is going to just come in like this, okay? And I can allow that to talk to the register file as such, okay? And then my ALU is now going to decide these operations. So I am assuming that you are able to read 2 registers at a time. So therefore, let me call this the A bus and this the B bus. Okay, and the answer from this can further go back to the same register file that I had earlier. Okay, now all I need to do, and of course the operands are going to come from here, OP of 1:0. So this is the advantage of combining these register files and building a register file with these kind of features. So this kind of a register file is a register file with 2 read ports and 1 write port. Okay, you can technically have 3 read ports, 2 write ports and all that. All that it depends on how many wires you are able to implement and allocate in parallel in order to do this operation. Okay, so now if I am able to do this kind of a thing, right, what do I need in order to write that sequence of operations, for example, where I wanted to do that addition. Okay, so let us say that 0, R1 and so on. Okay, now what I basically need to do is, data is coming from outside and it needs to be registered into one of these registers, right. In order to do this, I need to tell it which register, right, or in general when the ALU needs to operate on 2 operands, I need to tell it where this data is going to come from, and therefore I need to tell it the address of the 2 registers from which it has to read, right, and therefore I will basically get my read addresses. So this is a register file and this is going to have read address 1 and read address 2. Read address 1, right, read address 1 and RA2 is read address 2. Now I also need a write address because I need to, after doing some operation, I need to tell it where to write the address back, and therefore I need a write address as well. Okay, how many bits should RA1 and RA2 be? Okay, it turns out that in order to implement RA1 and RA2, I need to select, that depends on how many registers I have. It turns out, let's say in this case, we have R31, 32 registers. Therefore, this has to be 5 bits. Each of this has to be 5 bits. Okay. Now, having selected the input operands to the ALU via these registers, and also selecting the destination where the answer has to be written back, I need to now tell it what operation to do, and therefore I will now select operation, right. This is a 2-bit operation bits. Okay, so in general this is 4:0, 4:0, write address 4:0. So with every operation that is associated with this ALU, right, I can now collect all these addresses RA1, RA2, WA and OP, and so this is how many? 5 bits, 5 bits, 5 bits, and in this case 2 bits. Well, you could make it 8 operations, 3 bits, whatever it is, right? But effectively it is a 17-bit number that I can define as an operation code. An operation code that uniquely tells me what is the operation that needs to be performed in the processor in that one clock cycle, right? Of course, in the next clock cycle I can always change that. Now usually there is a control unit that is going to generate all these guys for you, the WA, RA1, RA2, WA and all that stuff, and along with the OP bits. There's a control unit. Now if I want only a fixed sequence of operations, this control unit can be a simple state machine, of course, that takes the clock, right, and generates a sequence of operations, right? But on the other hand, if I want to make this a more generic programmable unit, what is programmable? So till now the compute units that we discussed are purely hard coded to execute a certain kind of program. First case we did only addition, then we could do addition or this thing, but in some sense the control unit inside was determining what to do, right? Of course we brought the opcode out as primary input somewhere, but more or less these operations were prefixed because the registers were prefixed, what registers to do, what is destination, what is source, all that was prefixed. So it was a hard coded thing. Now in order to make this compute unit programmable, these set of operation codes that I want need to come from outside at some point, right? So therefore I can now define something called an op code as a primary input to this, where at every clock cycle I can give an opcode, right? And you are basically going to decode that opcode. What does decoding mean? You're going to figure out which is the source register, which is destination register, what is the operation, and then go ahead and perform that operation, right? This could be a primary input. Now where does this input get fed from? It gets fed from the code memory, where I store the program in a certain sequence, and what gets stored in the memory? It's a 32-bit number per address that is going to store the opcode, and that opcode is what we saw as a mnemonic in the earlier part of the course, right? So I can now interface this to a memory which will feed opcodes to you, and I keep fetching one opcode at a time. I decode, I execute, and then I go fetch the next opcode and stuff like that. As long as you don't have to go back to the memory and you are able to contain all your operations with the registers that you have, well and good, there is nothing to worry. However, in some cases you may have to write this data that you get from the ALU operations and all back to the memory because you don't have enough registers, right? So like I told you, it's only the context of around some certain operation you can store that data in registers. Beyond that, if you need, then you need to go back to the memory, and therefore the data can also go back to the memory, and therefore data itself can come from what is known as data memory. So this is where what I am going to call as code memory. Okay. So the compute system generally looks somewhat like this. You have a data memory, you have a code memory, you have a register file, you have an ALU, and you have a control unit that is going to decode these instructions for you and do this fetch, decode, execute in a cycle, one after the other, day in and day out.